Problem 2. As shown, the radius of the large circle is equal to the diameter of each of the 4 smaller identical circles. So here, okay, let me enlarge this. We have a large circle around, and then we have these 4 smaller identical circles. And as you can see, they do overlap. If the shaded area is labeled as S1 and the unshaded area is labeled as S2, then what is the ratio between these two areas? So here we don't have a exact value. We don't have like a length, we don't have like a particular area, but we do have a relationship. So we know that, right? So the diameter of one circle is equal to 2 times the radius. So what it's basically saying is that the radius of this large circle is 2 times that of the smaller circle. So why don't we first call, let's just give a variable to this radius. How about r, right? R stands for radius. Great. So if this is r, then we can use the rest of, we can easily figure out how to express the rest of these parts. But the hard thing is if you have, say, pi r squared, right? This is the total, all right? And now you're trying to have S1 to S2. Like this just doesn't work. So, but what is the hardest part that's blocking you from doing this? Well, the hardest part is these irregular shapes right here. So these little leaf-like shapes, that's not something that you've been taught how to solve. You don't know how to find the areas. You just don't know how to deal with them. So what you can do is shift, right? So what you can do is shift the different plate. We can shift these shaded areas into different parts in the figure so that you don't change the total amount of shaded area, but you just put them in other places where it looks more solvable. So here's what I mean. Why don't you first cut each of these, right, in half? This is another example of the second solution we talked about in the first video on the lesson, cutting and filling. You can move each of these to the edge of their circle. So you can move these to here. So this is a shaded part. You have this. So this becomes a shaded part. And here and here. So this is, and another thing we talked about was a holistic approach. Well, sometimes that's not the case. In this case, it's sort of the opposite because here, maybe you just didn't know how to figure it out because you didn't know how to put these leaf-like shapes in. But if you just take them apart in half, it's much easier to fit. Now you have a square. So this should be much easier to solve. So the shaded part then, if this entire so the total, this entire thing is equal to pi r squared, right? And now what about the shaded area? Well, the shaded area we could do first unshaded, this unshaded square in the middle. Unshaded square in the middle, and that would have a, well, if this middle part is unshaded, it would have a, you could have 4 triangles form. All right, and that is how you can solve this unshaded part. You could do r squared times 1/2 times 4, and then you would have 2r squared. So this unshaded part we can replace with S2 because it says that unshaded areas is S2. So what about S1? S1 would just be the total, this subtract this. So after removing 2r squared from this equation, we will have 2 squared minus r squared minus multiplied with the difference between pi and r. So now what are we trying to find? We're trying to find the ratio between S1 and S2. So if we put S1 on top of S2, which is r squared multiplied with pi minus 2, right? That's on the top, and on the bottom is 2r squared. 2r squared and r squared and r squared gets canceled out, and we have pi minus 2 over 2. That would be equal to 1.14 over 2, which in the end is equal to 57 over 100. So our final answer would be 57 to 100.